Okay, so we're going to be talking about conservation of momentum. And we're going to look specifically at the bottom of the problem set. So we're going to be getting after some stuff dealing with bumper cars. So I'll try to create a similar example, not exactly the same, but similar. So when we have this type of problem, we're going to luck out because we're going to have a smaller mass making contact with a larger mass. So let's just keep it really simple here. Let's just say it's 1 and 2. And then let's say that this one has a speed of, let's say, 4, and this has a speed of, let's say, 2. So that's going to be our setup here. This we can give these things special names in just a minute. Then we're going to have a collision, fire, explosion, and then afterwards we want to figure out what their speeds will be. Now it's not going to be as simple as just the arrows switching. Now if the masses were the same, we could just simply switch the velocity arrows and that would be it. There are a couple things that we need to keep in mind when you have a collision. 1. They push on each other equally. So at that point of collision, the forces are going to be equal. 1 doesn't push more on 2, and 2 doesn't push more on 1. The forces are equal. That's Newton's third law. Action-reaction pair, equal and opposite. 2. The momentum that we have coming in will be equal to the momentum that we have after the collision. That's the second thing that is conserved or equal. So what we can do then is, based on the fact that the momentum is conserved, is we can say that we have, this little mass, and then we'll designate its velocity little v, in addition to the big mass, which will designate its velocity big V. These are both initial conditions. Will be equal to the little mass times the velocity post-collision plus the big mass times the velocity post-collision. So we can put in the numbers that we can put in at this point. We could put in 1 and 4 here, and we could also put in 2 and 2. And so we'd end up with 4 plus 4, or 8 for the amount of momentum prior to the collision. So we can be sure that after the collision that it will have 8 for its total momentum. The problem is we're not really sure what the velocities are. So we'll kind of put in as much as we can. We could say 8 is going to be equal to 1 times little v prime plus 2 times big V prime. Now keep in mind that little v and big V are just like x and y. There really is no relationship between these two things. And so it would be incorrect to think that just because they're both v, we can just work with them as one thing, like x or y. So we're going to be forced to do a little bit more work than you might expect. So at this point, there's one last thing that is conserved or equal, and that's energy. So the energy before is equal to the energy after. So we can then say whatever change in velocity, whatever the difference was in the velocity prior to the collision, which will be 2, will be equal to the difference in the velocity post-collision. We also know that the 1 kilogram object will slow down, so we can predict a slowdown for its v, and we can also predict that the 2 will speed up. And we can say that the final velocity will actually be 2 apart, just like the initial velocities were 2 apart. So if we want to state this mathematically, we can, and we can say something about this. We can say the difference in the velocities before, which would be little v naught minus big V naught, is going to be equal to the opposite after the collision. So little v prime minus big V prime. So before we said the difference was 2, and then we can distribute that negative, and then we can kind of rearrange this in terms of big V and say 2 minus little v. So afterwards, if we find little v, we know that big V will be faster by 2. That's what we're saying mathematically. So we can use that expression right here to replace big V. So if we put in 2 plus little v prime right there instead of big V, and then we just write everything that we had before, 8 equals little v plus 2 times 2 plus little v. We can then distribute algebraically and get 4 plus 2 little v prime. And don't forget, we still had a lot of stuff over here. So if we add those together, we get 3 little v prime. 2 plus 1 is 3, plus 4 equals 8. Then if we subtract 4 from each side, we end up with 4 is equal to 3 times little v prime. Then all we have to do is divide each side by 3, and we get that little v prime is going to be equal to 1 1/3. So we then take that back up to our picture, and we put in its velocity of 1 1/3. That would match our prediction. It said it was going to go down. So then we can take that and plug it into our expression, 1 1/3, and we end up with 3 1/3 for the other velocity. And that also matches our prediction that we had. So when we're all done, we can get 8 by checking it. And so we're going to take 1 1/3 plus 6 2/3, and we end up with 8. And so it does equal 8, and we know that we did it right. And so that's our check. And so that is how we do this bumper car conservation of mass problem. A little longer than I wanted.